Howdy, we are the Aggie Warners, and this is our final presentation. Our team is comprised of 4 urban planners and 3 computer science students. Our problem statement is as follows. By federal law, trains must sound their horn at each crossing, and in Nolanville, the train track runs through the center of the town, and we're trying to solve this problem. The trains traveling through Nolanville creates safety concerns, traffic delays, and irritation to residents and motorists. So some work related to Aggie Warners is iPAWS. iPAWS is an ultrasonic equipment that picks up information and sends the status of the train arriving in real time to a motherboard, essentially. And the types of data that are shared is through emergency alert systems and wireless emergency alerts, WEA. The success of this example has allowed us to offer a solution to the intangible effects the city faces that are caused by the train in Nolanville every day. In analyzing the cause of the train running through the middle of the town, we are able to prioritize our focus on safety, enhancing communication, and community connectivity within the city. Our primary objective is to solve the problem of traffic congestion while also improving the safety and community connectivity within the city. Our secondary impact or long-term impact is to create a quiet zone in central Nolanville.
All right, as far as goals and objectives go, each member of our team was paired with activities within their field of expertise, meaning the urban planners would work on advertising and public engagement, whereas the computer science majors would focus on software-related tasks, such as choosing the right sensor, setting it up for testing, and analyzing the results. Throughout this project, we had 4 major tasks we aimed to follow. First was to choose the right software that would be relatively inexpensive and work under any weather condition. Secondly, trial run where we would test our software and make sure we were getting the results we aimed to get. Third, evaluate data where we would analyze how accurate our technology is. And finally, finalize the project the best way we could. And we were able to accomplish so much with what we were given, from finding a sensor that would work under pretty much any condition to understanding and preparing for pretty much any setbacks we came along the way.
So our overall design is comprised of 5 main components, as you can see in the picture. The first one on the far left is the sensor, and this is what is placed on the track. And essentially what it's doing is it's recording the distance between the sensor and the train and giving us the time during which the train is passing. And then the next component, which is the train database, essentially stores the data that is recorded by the sensor. So just to kind of explain what it might look like, the train database might have 2 columns. One column would be the time, and the second column would be the distance from the sensor to the train. And then the third component, which is at the top here, is the user database. And this will be storing the names and the contact details of any individual in the Nolanville area who signs up for a train notification system. And then the software, which is kind of the main component that ties in a lot of these other ones here. It utilizes the data from both the train database and the user database. And from the train database, it calculates the time at which the train will arrive at the crossing and then sends a message to all the users in the user database with the help of this thing called a Twilio API service. And so this service has been integrated into our code. And essentially what we can do is we can automatically send messages to all the users in the database with any sort of message. So for example, we might send them all a message saying the train will be arriving in 10 minutes.
To demonstrate our solution, we used an ultrasonic sensor and a Raspberry Pi. An ultrasonic sensor can send sound waves and detect the distance that the object is from the sensor. It does this by transmitting ultrasonic waves and detecting the time taken for the sound waves to reflect from that object. And we also use a Raspberry Pi, which is basically a mini computer. And this is going to be used for to program the ultrasonic sensor and read the distance of the object from the sensor.
Here are some of our earlier alternative tech solutions to creating a train warning system. Our primary alternative involved using a camera to capture images of the train at regular intervals and running the images through a machine learning algorithm to determine if the images contain a train and then signaling the Twilio API accordingly. The second alternative was to just use an infrared sensor and output a signal to Twilio above a certain threshold, similar to what our current ultrasound sensor does now. The last alternative involved using two sensors spaced apart and using the distance between them and the time between train readings to estimate the speed and estimated time of arrival, and include that in the text notification. Each alternative would eventually trigger the Twilio service, sending a text message to all registered users. In order to optimize the use of the sensor, we ran a test on it. The features we looked for to determine the sensor's accuracy were the distance from the sensor to the track and the distance from the sensor to the crossing. The output of our model was the error in the arrival time of the train at the crossing. Our original plan was to do a test run of our system using the train that runs through College Station, right next to Texas A&M University. Unfortunately, like most cargo trains, we could not predict when the train would come through the city. We ended up using a model train for our test run.
So for our demonstration test, we basically used a model toy train where we built up some tracks and we were checking how the train, when it passes through the tracks, how it affects the sensor readings. So as you can see here, we're checking the distance right here, which is the sensor to the track distance. And we're also checking the distance right here, which is the distance from the sensor to the crossing. So we know the length of each of these tracks. So we know the distance the train is traveling through these tracks. And we were varying the distance right here of the sensor and the track to see how it affects the sensor readings and how accurate it is, how the accuracy is affected by it. Now we'll play the demonstration of our test to show how we were testing our sensor. So as you can see, the train is passing through the tracks, and when the train is passing through the sensor, it is basically making sure that when the distance between the train and the track is at a certain distance, it is going to send text to the phone telling the user that the train has arrived. And the purpose of this is to really show that it's not going to detect when the train passes. As you can see from the other side, it doesn't detect the train, because basically we want to make sure we just detect the train passing through the track and not some other object. And this is really the basic use of the sound waves, helping us know what is the object that is passing through the train track at that point. And you can also see a picture of how this text is sent to my phone.
So looking at the figure on the left here, it basically shows the relationship between the inputs and the outputs. The inputs are essentially the sensor track and the sensor crossing, and then the output would be the error. So the idea here is that if you just look at the first two graphs here, so this graph right here and this one right here, what we can kind of see is that again, just to reiterate, the sensor track is the distance from the sensor to the track, and the sensor crossing is the distance from the sensor to the crossing. But if we take these two graphs and we expand it up, so that is essentially these graphs on the right here. What we can kind of see is that they're essentially the same thing, but they have a regression line. And so if you just look at the scatter plots, we can make out that the lower values of the sensor track, so those are these values right here, are all kind of grouped together at the bottom range of the error. But whenever we increase the distance like this, we see that the error actually increases. But on the other hand, if we look at the graph on the bottom here, as you can see, the values, even though we see these values here, and we see some higher values up here, that's why we have kind of a regression line that is sort of trending up, but at the same time, we can see that they still tend to line up in sort of the same kind of range. So even if we increase the sensor crossing distance, there isn't necessarily a huge spike in the error. And so kind of the reason for doing this is to demonstrate that we can optimize our system when we set up the hardware at the actual train tracks, and we can look at different variables and see how they actually impact the error. And this will allow us to adjust for kind of the arrival time, the estimated arrival time when we send out notifications for when the train is arriving.
For our final test, we went ahead and we went to the train tracks in College Station near Texas A&M, and we set up our system, as you can see in the picture on the right. We attached our Raspberry Pi and sensor to a tripod stand and a power bank, as you can see as well, to power up the Raspberry Pi. And we were basically trying to see how far the sensor needs to be kept. And since the sensor has a range of 13 feet, we wanted to see how close that's going to be from the train tracks, and if can we even use this sensor. So we realized that we would need a more advanced sensor which has a higher range, and also we were seeing if we could actually use this just to demonstrate our final test, and we plan to do that in the future.
So basically what we really want to stress here is that this is going to be very easy to implement. The software is easy, it's simple, it's a Raspberry Pi. Access to the hardware is readily available, and there's no physical interference or radio interference with the train itself. And it's, most importantly, it's really cost effective, and so it's going to be very easy to implement in other cities and other places that have this same problem that Nolanville is having with the train interfering with its crossing systems. And it should decrease traffic, and it's very low maintenance.
Moving forward with the project, we have discussed some ideas that future Aggie Warners members could implement to supplement our existing warning system. As you know, the existing warning system uses an ultrasonic sensor to detect the incoming train, which immediately sends notifications to Nolanville residents. The problem is, if some Nolanville residents do not own a smartphone or decide to opt out of the system, they will not be able to receive any of the warnings. To address this issue, we have been researching physical warning systems that would be placed at the actual crossing. This warning device would activate a few minutes before the train arrives, unlike the existing gate and flashing lights, which currently only activate 20 seconds before the train reaches the crossing. The next supplemental idea is individual warning devices for emergency workers. This device would not only help emergency vehicles avoid getting stuck behind the train, but would also improve safety conditions. If a vehicle collision were to happen at an intersection near the train tracks, emergency responders must be able to safely clear the tracks of any debris. The warning system will give emergency workers more time to clear the tracks when a train is approaching, so they can get back to a safe area. Ideally, both of these supplemental warning systems will also use the ultrasonic sensor as well. We also laid out the next steps that we believe the future Aggie Warner members should follow to expand this project. The first step would be implementing the existing warning system that we have proposed in Nolanville, allowing them to gather data over a longer period of time. Once the system has been in use for a while, they can receive feedback from the residents and supplement the project with the two warning systems discussed in the previous slide. Finally, the final step would be implementing the complete final train warning system. Thank you. Are there any questions?